Continuing with the universal law of gravitation. To remind you again, what is the universal law of gravitation? A force between two masses
6.67 times
is directly proportional to the product of the masses and inversely proportional to the square of the distance between the two of them. Square of the distance means from center to center, and then square it. And that force was G, capital G, M1, M2 over D square. And we applied it for our force, the force that is acting on me. All right, so if that is the earth, and that is me, not to scale, that is mass, my mass, and the earth's mass. What's the force between me and the earth? What's the force with which I am being pulled by the earth? According to Newton's law of gravitation, that force is capital G, capital M, small m over, what's the distance between me and the earth? The radius, so the radius square. Okay? That is the force of gravity that's acting on me, and till last class, what we were saying as a force. What's the force acting on me right now by the earth?
Contact force.
No, what is that force? How do you find the gravitational force? The so-called weight. mg. So this is what we regard as mg. And where g is the acceleration due to gravity where we are, correct? So at this part, the g is there. Now if you compare these two equations, you can see mass is gone, and we see a very important relationship between capital G and small g. That's a very important relationship between small g and capital G.
What is capital M?
The mass of the planet. So in this equation, what does capital M stand for, as he said? Mass of the planet, not necessarily Earth. It can be for any mass. What is this?
The radius.
Radius of the planet. What is capital G? 6.67 10 power minus 11, the universal gravitational constant. And what is the small g? Acceleration due to gravity where?
On Earth.
On the surface of that planet. So this is the equation for any mass. So this has a gravity. This marker has a gravity. All right. So if this mass of the mass of this thing, radius like to the center, g. What's the g on the surface of this marker for the marker? Okay, so that is basically this equation. This equation is not only for Earth, it's for any. It's for any. Now if you cross multiply this, we get gm is equal to gr square. So wherever you have gm, you can actually write gr square instead. This is capital M, which is mass of the planet. So if you multiply capital G times capital mass of the planet, it's the same as g, small g times radius of the planet square. Okay? Now how do you use this equation? A simple example. Suppose for the Earth, if this is the Earth, GE is GME over RE square, correct? See, I put subscripts for you to understand that. Now suppose there is another planet which is half the radius of the Earth. And has twice the mass of the Earth. What will be the G on that planet? What will be the G on the surface of that planet? So what you do is pounce onto this equation. So let's write down that equation. GP on the planet is GMP, Griffin, over RP squared. Now replace MP with this. Replace RP with this. What do you get? Now what do you have? This is G 2me over re square over 4, correct? Now pushing all the numbers around, it will be 8 on the numerator, gme over re square. What is gme over re square? What is that?
GE.
So this means it is 8 times GE. So what do you understand from this little comparison? If a planet has twice the mass of the Earth and radius half of that of the Earth, the G on that planet is 8 times that on the Earth. So if it is 9.8 over here, it should be 8 times 9.8. You understand how to work them out? Like, so if I tell you there's a planet that's got half the mass of the Earth and radius is triple that of the Earth, how do you find the G on that planet? Just this is the process. And finally, whatever number comes out here, that is that many times. Okay? Clear? Now, the G on the surface of the Earth, you know it is 9.8. But if I want to find the G over here, like what is the acceleration due to gravity at that spot? How much will I weigh at that spot? I know I weigh 800 newtons here, but how much will I weigh over there? Will I weigh more or less? Less. So how do you find that out? So instead of putting the mass over here, if I carry myself and put myself there, what are the forces acting on me? Downward, how much? According to Newton's law of gravitation, F is what? G, mass of the Earth, times mass of me over
Distance over distance squared.
how much is distance? What is the distance between me and the Earth?
AG R plus H.
R plus H, because this is from here to here is R, and then there's an H. So it will be R plus H squared. Okay? So it will be R plus H squared. You understand so far? And that is going to be my weight. And how do you write your weight? M times which G? Small g. Like, is it 9.8? Will it be 9.8 here? So you don't know that value, so I'll write G prime. It's a new G. You know that it's supposed to be smaller because it's further away, right? So it's supposed to be something different, not 9.8. So let me call it G prime. Now compare the two equations, cancel the masses. Now by cancelling the masses, you can clearly understand that it does not matter what mass is sitting there, the G prime over there is independent of mass. Clear? The G prime over there, the acceleration due to gravity at that spot does not depend on what is sitting there. Alright, simplify this, you get G prime is equal to Gm over R plus H squared. And I can replace Gm with what? Gr squared. So I can write this as GRE squared over RE plus H squared. So to find the acceleration due to gravity at that spot, all you do is this calculation. So this is an important equation. It tells you the acceleration due to gravity at any height. So if I say that I'm 1,000 kilometers above the Earth's surface, and you know the radius of the Earth is 6,400 kilometers, can you find out what's the G prime over there? Substitute. So what is G prime over there? You know, small g is 9.8, which is the surface value. times RE. What is RE? You can't keep in kilometers, so we have to make it meters. 6.4 times 10 to the power of 6 meters. So it is 6.4 times 10 to the power of 6, and don't forget to square it. That's a very common mistake. In this chapter, the biggest mistake that students make is forgetting to square where it is needed to be squared. Over. What is RE? Again, same thing. So 6.4 times 10 to the power of 6 plus, what is H? It's 1.0 times 10 power 6. Again, don't forget to square that. Can you calculate this and let me know what you get? So the acceleration works out to 7.33 meters per second square, which is reasonably correct because it's 9.8 here and you've gone 1,000 kilometers, and so having a value of 7.33 is understandable. Now, at what height do planes fly? Normally, like long distance planes.
50,000.
They won't go to 50,000. 35,000. I don't think they go 30, maybe 38,000. In kilometers, it's going to be 10 kilometers. In kilometers, it will be almost 10 kilometers. That's the height. So what will be the gravity at 10 kilometers height? How do you find out? Put 10 instead here. So basically, this is going to be like 10 kilometers with 1.0 times 10 power 4. Can you recalculate that and let me know what you get? So even at the altitude where the plane is flying, the G is not greatly different. You'll see it. Put 10 kilometers for height and tell me what you get. Do the same calculation with 10 kilometers instead of 1,000 kilometers. Use my calculator.
Oh, yeah.
9.76.
9.76, see, it's just close. So if you're getting 9.76, that's reasonable again. So gravity over here is 9.8, 10 kilometers height, it's 9.76, slightly off, but it's not greatly off. You see it? So the higher you go, the smaller the acceleration due to gravity value. Now look into this equation and let me know what you understand. Now, if h, if I go to a height which is exactly one radius away, if the height is equal to r, if the height is equal to the radius of the earth, what will happen to the equation? Then g prime is going to be g re square over, if h is also re, it'll be 2re, so whole square. So it'll be 4re squared. Did you get it? So what is the g there? It is just 1/4 of 9.8. The acceleration due to gravity value, if you go 6,400 kilometers upward, is only 1/4 of that of the earth. What if you go to a height of 2r? What if you go to a height of 2r?
Oh, yeah.
Go to a height of 2r.
199.
So it'll be g prime will be, so if you put 2r over here, the total thing comes up 3r squared becomes 9. So it'll be g over 9. Now, what if height is 3r? G prime will be g over 16. What if height is equal to 4r? Just 4 times the radius of the earth. G prime will be, you can see how the gravity values are changing. Now plot a graph. Plot a graph of acceleration due to gravity. Plot a graph. Keep yourself busy, then everything will be all right. Plot a graph of acceleration due to gravity versus height. And this is the surface. Zero height means you're on the surface. So on the surface, what's the value of acceleration due to gravity? 9.8. What if you go to a height of 1 radius? If you go to a height of 1 radius, what's the value of acceleration due to gravity there? It's a fourth of 9.8. So it's a fourth. What if you go to a height of 2r? It's a ninth. What if you go to a height of 3r? It's a 16th. What if you go to a height of 4r? It's a 25th. You can see how exponentially it is coming down. So at a height of r, it is g over 4. At a height of 2r, it is g over 16. Or g over 9. And then g over 16, and then g over 25. So you can see the acceleration due to gravity comes down exponentially. So by the time you go to 4r heights, it's almost tiny. So what is the acceleration due to gravity here? At 4r, distance of 4r. 4 times 6,400. 0.39 meters per second square. Pretty small. So you can see how the acceleration due to gravity value goes down. So if I ask you, what is the acceleration what is the height where the acceleration due to gravity is 2 meters per second square? What do you do? What do you do for that? How do you find the height where the acceleration due to gravity is 2 meters per second square? You go back to this equation, plug in this as what? 2, that will be 9.8. You know this, you can find that. Okay? You will get it, of course, in meters, and if it is required in kilometers, then you can change it later. Any questions on this? This is clearly telling you how the g value, acceleration due to g value, will change as you go to different heights. The maximum acceleration due to gravity is on the surface. Now if you go into the earth, the story is totally different, because then you're not using the entire Earth's mass. You're sitting on a smaller Earth. As you go downwards, you're sitting on a smaller and smaller Earth. The rest of the Earth will become like an atmosphere for you. And so when you go right to the center of the Earth, the acceleration due to gravity is 0. Okay, that's for a different reason. But above the Earth, this is the equation that tells you the height. Is that okay? Questions? Question? No questions.
What is G prime?
That is a new G, whatever it is. The G prime is the new G anywhere else. Like, as I said, at what height is the G going to be 2 meters per second squared? So that's a G prime. It's just a G, it's different symbol. That's it. Yeah.
So, no matter how far an object is from like Earth per se, will it always have a value of
Yes,
gravity?
you're right.
Okay. So
It's always going to have a value of gravity.
Okay.
Unless you are somewhere between. Let's say this is the Earth. This is the Earth, and this is the Moon. If you're here on the Earth, it's 9.8, right? As you go away from the Earth, the G is going to come down. Drop, drop, drop. Now, as the G value goes down, remember the distance from Earth to Moon is approximately 60 times the radius of the Earth. Okay, approximately 60 times. So as you go like this, it's going to very significantly drop to a very, very small value. But by the time you approach the moon, as you get closer to the moon's gravity will start pulling from there. When the Earth's gravity is getting weakened from this side, the moon's gravity starts getting stronger and stronger. So there will be a certain spot, closer to the moon of course, where the pull from the Earth and the pull from the moon will be. So what's the G value there? 0. So there will be a spot somewhere closer to the moon where the G can be 0. So which means if you fall a little this side, then you fall into the Earth. If you fall that way, then you go to the fall. Okay? Now, let's talk about orbital motion. What is this orbital motion? Now, to understand orbital motion, let me give you some more explanation. What is this? This is a marker. If I drop this marker from here, you see it's falling straight down. What is taking it down?
Gravity.
Gravity. Gravity is taking it down, right? Now if I take the same marker, watch me. Griffin, watch me. Now mind you, it's getting recorded. Your name is getting recorded many times. That's not a good thing.
I'm gonna go viral.
Yeah. Yeah. So, you know why your name is being recorded? Because you're sleeping. Yeah. All right. Now, if I throw the marker from here like this, what happened is the marker fell over there. Why did it fall?
Gravity.
Because of gravity. Now, if I threw it faster, what will happen? It will go further down and fall. And I'm trying to show you in a picture format. That's the Earth. That's me standing with the marker, not to scale. Okay? Because that is 6,400 kilometers, and so that is me with the marker. Now, what if I drop the marker? It falls straight down. Now, what if I throw the marker horizontally? It goes and falls there. Now, that again is not to scale because that is almost a distance from here to New York or further apart. So the marker goes from here and lands there, right? Now, what if you throw it faster than that? It will go and fall because it is falling anyway. It's falling, but it's landing further away. What if you throw it faster than that? It will fall there. If you throw it faster than that, it will fall there. What if you throw it just at the right speeds? It will fall, hit your head, keep falling. It will go around and come back and hit you because that is called orbital motion. How fast will it have to go? We're going to do it right now. So how fast should I throw this marker so that it will come back? And of course, if it's able to come back, it will keep going. Nothing to stop it. Now, I can't do this with a marker because air resistance. Air resistance is definitely going to slow this down. No matter what I do, it's going to definitely kill the energy and then it will make it fall. Okay? If I throw it really, really fast, it will burn up. So air resistance can actually destroy the whole thing. So what you have to do if you want to really put something in orbit like a satellite, you have to go above the Earth's atmosphere and then do the same thing. You go above the atmosphere of the Earth, extends up to only around 100 miles. After 100 miles, 150 miles, there's no air. So if you take a satellite up to that height of 100 miles, 150 miles, it's not too much. If you look at it, you know, it's not too much. The height. The distance from here to Chicago is what? how much? 300 miles? Now, comparing that, 150 miles is not much at all, height-wise. So if you go above the Earth's atmosphere and then project something with a required speed, it will keep orbiting. That's exactly how satellites are in orbit. So what you need to do is go above the Earth's atmosphere. Of course, this is above the Earth's atmosphere anyway. Look at that. If this is 6,400 kilometers, That's a lot. It's more than 1,000 kilometers. You don't have to go that far to project a satellite. So if a satellite is projected, so let's talk about a satellite. Or let's talk about the same thing here. Let's talk about this marker. Is that satellite going in circular motion? Yes? How many forces are acting on it?
2.
Which are the two? How many forces are acting on the satellite or on the marker if it is orbiting?
Gravity.
Gravity and?
Normal reaction.
It's not touching.
Centrifugal force?
Ethan, what is it?
No, that's
Centrifugal force.
Good, that's a net force. How many forces? Only one force. There's only one force acting on the satellite, which is its own weight. When I threw this marker, what did you say is taking it down? Its weight. What was taking it down? Its weight. There was nothing else. So when a marker is falling but not reaching the earth at all, it is orbiting. How fast should you throw it? You should throw it at that speed. It will have a weight acting downward which provides the centripetal force for it to go round and round. So what's the force acting on this mass m? The force acting on the mass m is gmm over r square. That force is the force that keeps it going in circular path. What is the force needed to make something go in circular path?
F equals GM.
That's a force, but what is the,
Centrifugal force.
which is what?
The net force.
Which is the net force, which is what? How do you, what's the equation for it?
No.
mv square over. Now compare these two equations. So this is the gravitational force on the satellite, and this is the centripetal force. So we know that gravitational force is the centripetal force. Knock the mass off. So it doesn't matter what is the mass of the satellite and all that. Doesn't matter what satellite you're putting up in orbit. Doesn't matter. See, mass is gone. One of the radius can be knocked off right there. So what is the v square? It is gm over r. What is gm, by the way? What is gm? gr square. Which is? So what is v? How fast should you go? Plug it in. 9.8 times 6.4 times 10 power 6. Tell me the answer for it. How fast should it go in order to orbit? 7.919 meters per second, which is 7.92 kilometers per second, which is approximately 5 miles per second. If I can throw something at a speed of 5 miles per second, then it will orbit.
That's fast.
Or how fast should I drive my car so that it will start orbiting?
Fast. 18,000 miles per second.
This is a speed with which I should drive not 5 miles per hour, 5 miles per second. If I can move 5 miles in 1 second, that speed will put me in orbit. But the problem is air resistance.
I've got a fast speed before.
Okay? Now, if I'm going to a height of, if I'm going to project a satellite, if I want to put a satellite in orbit, I go above the Earth's atmosphere, and let's say we went to a height of, 300 kilometers or more, 500 kilometers. Let's go to a height of 500 kilometers. How do you find out the speed over there? What speed do you need for it to go round and round? Come back to this equation again. Come back to this equation. What are forces acting on it? G M M over. Is that right? That's a force acting on the satellite, gravitational force. And what is it in terms of centripetal force? You understand that? Centripetal force is what? mv square over the radius of the turn. What's the radius of the turn taken? The radius of the turn taken is this, because it's going like that. So do the same thing. Cancel the masses. Cancel one of these. What do you have as speed square? Gm over r plus h. You can replace it as gr square over r plus h. Plug it in. It is 9.8 times 6.4 times 10 to the power of 6 over 6.4 times 10 to the power of 6 plus 500 kilometers. 5.0 times 10 to the power of 5. 5.0 times 10 to the power of 5. Can you do this calculation and let me know what is that speed? On the Earth's surface, it was 7.9 kilometers per second. Let's see from that point. Those are the places where the actual satellites are moving. You know, the satellites that are weather satellites, they're all going around that height. We can't put it lower than that because the atmosphere will actually slow it down. What's the speed? No, it should be slower. Or did you take the square root? Oh, I'm sorry. See, that's a common mistake.
No.
See, I forgot the square there. That's a very common mistake, I'm telling you. I can make mistakes like that also. See, I was looking at this, substituting it, and I didn't square it. And now at the bottom there's no square. So just be careful about those things and do it. Is it?
7,647.
That seems right. So 7.63 kilometers per second. That's the speed of that satellite. So how do they put these things in that orbit? How do they put the satellites in orbit? How do they put the satellites in orbit? They take it in a flight, and then they start going higher and higher, and they start going higher and higher, faster and faster, and finally, so it looks like a rocket that is shooting up straight, right? So after it takes off like that, it starts turning, and it has to go to the height and the required speed. So what they do is they go to the height of 500 kilometers and reach that speed of 7.6 kilometers per second as precisely as possible, and they turn off the engines. Once they turn off the engines, once they reach that height and that speed, then they are orbiting. So they can orbit there forever. And then what they do is they detach the satellite, leave it alone, and then they start their engines and come off. So the satellites are left there, knowing that it's going to orbit again. So there are thousands and thousands of satellites in the sky right now. So many countries have put their satellites, and they're all orbiting, and they're all doing different jobs of checking weather, looking for mineral resources, looking for suspicious activities like military, spy planes, spy satellites. There are a lot of them going on right now, and they're doing the work. How fast are they moving? They're moving really fast. Look at the speed. Now if we use the formula V equal to R omega, it will tell us how fast they are spinning. And also if we can replace the omega with 2 pi over capital T, that capital T is standing for what?
Time period.
Can you find the time period? What is time period equal to? time period is equal to 2 pi r, which is the circumference divided by the speed. 2 pi r, which is circumference divided by the speed. That will give you the time period, how long it takes. Can you find this out? 2 pi times r. Well, it's not r, it's r plus h. Because the total circumference is going to be that. So 2 pi times 6.4 10 power 6 plus 5.0 10 power 5 over 7627. And what is the time? You'll get your answers in seconds. So see, you can actually find the time period of the satellite. You'll know how much time it takes to go around and come back. You get it? Everyone should be pressing these buttons and calculating, because you will not be able to do these things all of a sudden unless you practice it. Now you know the answers are these, so if you're able to do this and get the answer without any trouble,
5,684.
that looks right. 5,684 seconds. Can you tell me how many minutes it is?
94 minutes.
94 minutes. So it's a little over 1.5 hours. It's a little over 1.5 hours. So 94 minutes. So if it crossed at 10 o'clock above your head, it will come back again after spinning around the earth at 11:30. Right? So the time period of that satellite is 94 minutes. Now there are so many satellites, not always at this height. You can have different heights. According to the heights, they are going at different speeds. Now there are some satellites. So these are the satellites which are used for what? Weather, spy, mineral resources, and all those things. So there are so many satellites that are spinning at tremendous speeds, and they're doing this. There are some satellites that are parked in space. They're called parked orbits. What do you mean by parking? Parking means like you put a satellite and it'll stay there.
Geosynchronous orbit.
Geosynchronous orbit. Good. That's called, what is a geosynchronous orbit? It goes with the Earth. It's like parking your car. Where did you park your car?
Parking lot.
Yeah, in the parking lot. So I parked my car over there. And whenever I want to look at my car, oh, that's there. Where's my car? It's right there. So I can point it in the right direction. Is your car moving? Your car is moving at a speed faster than the speed of sound, and so are we. So we are all moving because the earth is spinning. So your car is moving and you're moving, but with respect to you, the car is not moving, right? And that's exactly what we're doing. So what is this parked orbit? A parked orbit is an orbit. It is far away. It is far away. And it is so far that it is always above a certain spot. In other words, it is spinning with what time period? What time period? Period of the earth, which is? So the time period of this one is 24 hours. Now can you find out what height it is supposed to be? That's a challenge. So what are you going to do now? We're going to use the formula GMM over R plus H squared. That's the formula for the gravity on that satellite. Is equal to, see, look at this, I'm using omega right here. M R plus H omega squared. Why I'm using omega? Because I want the time period to come in. Griffin. So you can see from here, now gm is gr square, so gr square over r plus h cube, because I'm bringing that here, is equal to omega square. And what is omega? 2 pi over t. So if I put omega 2 pi over t, you get the equation gr square over r plus h cube, which is omega square. So it becomes 4 pi square over t square. And what are you trying to find out? The height. This one. How do you bring the height from that equation? So you have to get r plus h first. So from here, let's see how it happens. So gr square. So what is r plus h? R plus h cubed is equal to what? It will be gr square times t square over 4 pi square. Get this, and then get r plus h. And then get h. So you got multiple steps to do. Find this first. Then take cube root. How do you find the cube root? To the power of
3.
1/3. You find the cube root by taking to the power of 1/3. Do that. Find this out first. Now 24 hours. You can't keep 24 hours. You have to put it in. Yep. So this is going to be 86,400 seconds. Put that there and square it. Let's see who gets the height first.